Hello everyone, my name is William Hawk, and this is
Kevin Flournoy.
And we are here to present our co-plan and co-teach. Unfortunately, due to time restraints, we were not able to do this in class, and so we've created this video for you.
We're going to take this opportunity to conduct our lesson as if you are a fictional class of high school students, as opposed to just a video of us talking to an empty classroom. Say a little bit about our hypothetical class of students, Bill.
Our class is an AP Physics class of 11th and 12th graders. They are expected to have completed or currently be enrolled in a calculus course and preferably have taken at least 1 year of non-AP physics already.
So pretend that you are our class of AP Physics students. Let's talk about what we're going to do in this video today. We're going to go over two main problems. We're working in a collision module, which is something that might come up about this time in the school year for this class. The first problem is going to be one that the students have had a lot of practice on, a review idea of one-dimensional collisions. The second one will have a little bit more hand-holding because we started doing questions like this in lecture today, and it's about a two-dimensional collision problem. Now, what do our viewers need to know when they watch this video, Bill?
For our students, we would encourage them to be able to pause and rewind the video at any point if they had missed a concept or needed further instruction in it. For you, since you may not be following along and actually needing the wait time that we're giving you, feel free to just skip ahead of that wait time and continue on with our actual presentation.
All right, class, what we are about to see is a cue ball, that's the small white ball on the left, be struck and travel across the table to collide with the large black bowling ball that you see on the right. The cue ball, as you can see, is much smaller, has a much smaller mass than the bowling ball. And so what I would like you to do is write down a hypothesis about what you think the result of this collision will look like. Do you think that the cue ball will bounce off without the bowling ball moving? Do you think that the cue ball will come to rest and the bowling ball will move? What direction do you think these movements will take place in? And write down any other thoughts or questions that you may have regarding this setup. So take some time now to go ahead and write down those hypotheses and questions, and we will continue from there.
Alright class, now that you have written your hypothesis about what's going to happen after the collision, I would like you to justify that hypothesis by writing down some of the big ideas from physics, any sort of laws or other physical properties that you can use to justify your ideas of what will happen. I'd like you to draw a diagram of the system both before and after the collision has taken place. And finally, I would like you to write down any questions or any unknowns that still exist in the problem. So let's just take a little bit of time to do that now.
Alright class, now that we have created our hypothesis and we have supported that hypothesis using the laws of physics, and hopefully we've drawn some free body diagrams to help support that hypothesis as well, we're going to actually watch the collision take place now. I'd like to watch very carefully because it is very quick, so here we go. Just in case you missed that, let's go ahead and rewind a bit and watch it one more time. And let's just try to go through it frame by frame. Now that you've viewed this, I would like for you to record the observations of what you have just seen. So take some time now to write those observations down. I would like for you to pay special attention to the velocities of both balls right before and right after the collisions. And go ahead and take some time to do that now.
Alright, so now that we have seen the demonstration in action, let's go ahead and take another look at some free body diagrams. I'm just going to start these off for you, and I would like for you to finish filling in these diagrams on your own and bring them with you to class. So, originally, before the collision, we had the small cue ball and we had the large bowling ball. And then after the collision, we still had the same two balls, but their velocities were definitely different. So, some information that you're going to need to be given in order to solve this problem is that the mass of the cue ball, that's the small white ball, is 0.17 kilograms, and the mass of the bowling ball is 5.44 kilograms. The last piece of information that you need is that the velocity of the cue ball before the collision was 3 meters per second. So, taking that information and the video that you watched, I would like you to find two things for me. I want you to find the velocity of the cue ball after the collision, and I would like you to find the velocity of the bowling ball after the collision. Now, this is going to require a bit of thinking on your part, but if you look back at the big ideas that you had come up with and take some time looking at it, I'm sure that you could find equations that will let you find both of these values. So go ahead and take some time to work on this, and good luck.
Alright class, now that you've started making your outlines and started working on this problem, I just wanted to see if there was any guidance that I could give. For starters, we know that there are two unknowns that we need to find. So that implies that we need at least two different equations in order to find them. Since we've been working with momentum so long, I'm sure that you know that you can use the conservation of momentum. However, you will need to find one other physical property to use in order to solve for these unknowns. Also, it's important for you to know if this is an elastic or inelastic collision, as that will help guide you to what physical property you're going to need. go.
Welcome back. After having worked on that problem for about 10 minutes, you should have made a lot of progress, and maybe you're wrapping up your answer right now, or you got to a place where you're stuck and you're leafing through your notes. Both fine. We intend to take this problem and bring it into next time we meet in class tomorrow. So this is what I want to see from your work in this problem. You're going to do a written comparison between what you observed in the video and the math result if you got one. So compare what you see with your math results. Here, we're going beyond just getting an answer and making sense of it. A good comparison might discuss differences, similarities, and further thoughts. Surprise us, and you might have something to share with the class tomorrow. Or, if you got stuck, describe where you got stuck. Your description could be in words, or you could highlight a certain equation or make some notes, or ask a question. No matter what you want to show to me tomorrow in your journals, you have to have it boxed. I want you to come to class with something ready to go so that we can continue this discussion.
Recording.
So now that you've finished up the first problem, go ahead and start a new piece of paper and open up your notebook to today's notes that you got in the lecture in class, because we're talking about a two-dimensional collision problem. And as you can imagine, with 2 dimensions compared to 1, there's more than twice as much work. So you'll be referring to those notes quite a bit. Let's go ahead and check out the video and look for certain interesting conclusions about where the balls go. It turns out there's a pretty powerful and generalizable result that we'll see when we do this math. Table down in the student union. Take 3. Here you can see our experimental apparatus, better known as the pool table down in the student union. Mr. Hawk and I had a very fun time setting this up and bringing something that should be pretty familiar to you guys to the physics classroom. There's a reason why this is such a common explanation for perfectly elastic collisions. The first time we set this up, I sank this shot, and then it took us about 20 more takes, and we eventually got one of the fellows that was playing next to us to sink it, which you can see right here. Okay, let's note a few things about these pool balls. Perspective plays a little bit of a trick on us, but this ball is not lined up with the 8 ball and the pocket. It's at about the same angle I gave you in the problem, 53 degrees, from this x-axis. Secondly, notice that the ball isn't centered on the table. Well, in the givens that I gave you, it was a 45-degree angle from the collision to both pockets. So, the fact that I make this shot and I give you more friendly numbers but get a similar result, what can you say about that? We'll be talking about that in class tomorrow. Let's look at it one more time and then I'll show you my diagram. Now that you've had a chance to make your own diagram, go ahead and compare it to my diagrams of that pool table problem that I have here. Let's start on the left-hand side with this initial diagram, I for initial. Well, before the balls hit, we've got mass 1 traveling toward mass 2 with an initial momentum. Notice that I label it momentum for particle 1, initial, with that vector symbol there. Object 2 is at rest, so I could add here maybe a note to self that this is equal to 0. note to self. That's good news because that's one less thing that we have in play and one less variable perhaps. Lastly, I'm going to specify this angle here, alpha, that is a certain measurement compared to like the side of the pool table. And I'm lining up my x-axis here with positive going in the direction of motion, calling it x. If you were doing your own diagram and label it something different, that's fine too. Make sense of it and include on your diagram what I have that you didn't. Let's go on to final. After the two collide, they're going to be going off at these different directions. I have the same axis here. It's important to always have the same axis in both problems so that you can compare final to initial properly. I'll give you the values for these angles just below. And also I've included here in blue the initial vector just for perspective. Notice that this is not actually occurring in the final. It just kind of completes the picture. You know what I mean? You may want to pause the video here and do your comparisons before you move on and take down these values for the angles and the initial velocity. Okay, here's our masses. They're equal for both of the billiard balls. Here are our angles. These will only make sense if you're using the same diagram that I did. So please, if yours have different names, put them in the right place. Oh, I said that I'd have my initial velocity here. Momentum, 1 initial. Oh no, I don't want to say momentum. It's easier to speak in terms of velocity right now. Let's say velocity, 1 initial. And I'm not going to put the vector on it because it's not even going along a nice axis, equals 3 meters per second. Okay, you might want to pause again and take these numbers down, make sure that they're matched up correctly. And you can see here what I'm asking you to solve for. Give me the scalar quantities of the final momentums, please.
Recording.
So that wraps up my guidance on this problem. Use my diagram, consider my hints about where this problem is going to go, and now you're going to work on this problem for homework. And I'm going to want to see your work very clearly. So stop where you are on this page and leave room for our lecture tomorrow. Turn the page and start your work on this problem. That's so I can see where your work is and you have room for the work that we do together in lecture tomorrow. Good luck.
Ready?
Yeah.
Here we go. All right, class. I know you still may be working on that last problem. Feel free to take as much time as you need to complete it, but we're going to go ahead and start wrapping up the video lecture now. So, for tomorrow, we need you to bring in your boxed response for question 1. That would either be your comparison along with a numerical result, or a description of how you got stuck in the problem so that we can talk about it tomorrow. We also want to see your work on a separate page in your notebook that you've been doing for question number 2, and along with any questions or concerns you have about that.
So to our physics class, we'll see you tomorrow. And to our Cal Poly class, thank you very much for watching this video. We look forward to seeing you in class as well. And if you have any feedback for Bill and I on this video, we'd love to hear it. Thank you again.
Thank you very much.